Welcome to clickmyproject.com. Our product title is a process-tolerant low-voltage inverter-based OTA for continuous time sigma to delta ADC. Let us see about abstract of our product. Receivers are being digitized in a guest for flexibility. Analog filters and programmable gain stages are being exchanged for digital signal processing at the price of a very challenging analog to digital conversion. Inverter-based implementation of operational transconductance amplifiers is an attractive approach for low voltage realization of analog subsystems. However, the high sensitivity of inverter like amplifiers performs to process and temperature variance limits the achievable performance of the whole system across process and temperature corners. In this proposed implementation, a tuning technique is proposed to maintain the inverter based amplifier performance across the process and also the temperature corners without requiring additional voltage headroom that required by the inverter circuit. The introduced technique is used to implement a third order continuous time sigma to delta analog to digital converter. The main building block of the implemented analog to digital converter is an inverter based amplifier. This makes the resulting analog to digital converter easier to scale to different technology nodes. A 74 dB signal to noise and distortion ratio is achieved for a signal bandwidth of 64 kHz at a sampling frequency of 6.4 MHz while consuming 400 microamps from a 0.8 volt supply in 65 nm CMOS technology. Next we see about the flow diagram of our product. In this flow diagram, the input signal is an analog signal. The process is analog to digital conversion, so the input signal is analog signal. Then that analog signal is fed into inverter based OTA stage 1 through a passive elements, and after that the output of the first stage inverter based OTA is fed into second stage, and also second stage output will be flow through the third stage of inverter based OTA. After that output will be fed into stage 4 inverter based OTA, and then that output will be getting the output digital signal block, before that through the RZDAC. Generally the digital to analog conversion is used in the ADC. Connecting digital circuitry to sensor devices is simple if the sensor devices are inherently digital themselves. Switches, relays and encoders are easily interfaced with gate circuits due to the on and off nature of their signal. However, when analog devices are involved, interfacing becoming much more complex. What is needed is a way to electronically translate analog signals into digital quantities and vice versa. An analog to digital converter or ADC perform the former task while a digital to analog converter perform the latter. An ADC inputs an analog electric signal such as voltage or current. Together, they are often used in digital systems to provide complex interfaces. Used in automotive engine controls. In electronics, a digital to analog converter is a device that converts a digital signals into the analog signal. An analog to digital converter performs the reverse function. There are several DAC architecture. The suitability of a DAC for a particular application is determined by three main parameters. First one, resolution, and second one, maximum sampling frequency, and final one, accuracy. Due to the complexity and the need for matched components, all but the most specialized DACs are implemented as integrated circuits. Next we see about running process of our product. In this proposed implementation is done in Tanner EDA tool in SEdit tool. First open the SEdit tool and create a new cell. After creating the new cell, we update the library file in the simulation parameter. After updating that, we draw the corresponding circuit as per the base paper. After circuit arranging, we click the run icon, then T-Space window will open. In the T-Space window, the generating data will be shown in here. The first one is normal input and output data are here, and next one is the T-Space window. This is used to generate the power of corresponding input and output data. So these are the input voltages and these are the power calculated, and also this is the time delay for corresponding output data. And then we click the run icon, the output WEdit window will be open. In the WEdit window, first one, the input and output data of the corresponding output, and this is the normal overall output. Then we click the expand chart, then the output will be separated in the format. So this is the corresponding output waveform. And next one, if you want to see the frequency value and also the FFT analysis for that corresponding output, we click the FFT, then the output will be displayed in the frequency as well as the dB ranges. So this is the overall input and output waveforms. And next we see the power output for corresponding input and output data. So this is the power output. The power range is around 30 microwatts. So this is the range, and this is the unit of corresponding output power. So these data will be shown in the waveform format. If you want that the FFT analysis for this, so click the FFT, then the output will be displayed. This is the power value, this is the input and output data values. And next one, the time delay values are calculated in the separate T-Space window, and that calculated values are stored in the corresponding folder, that is in the notepad format. So this is the values, what are the PMOS and NMOS parameters used here, and what are the time delays are getting here. So overall power consumption will be reduced and efficiency will be increased. Thank you for watching this video.